Oh, have I started the broadcast? There we have. Yeah. Right, we left off from this morning, and I gave you an activity to do. And the last thing of the activity, we were doing something that didn't work. Okay, so we were drawing a line using Freshening's algorithm where the gradient was greater than 1. And like the DDA, which we saw on Monday, it failed. Okay, so although our algorithms, especially Freshening's, very efficient, very simple, there are some modifications we have to do to them both in order for them to be of any use. So that's what we're going to be looking at today. Quite a short lecture. So I'll mention what modifications need to be done. You're going to have to do these for your assignment. So assignment 10, I'll give you the basic Freshenings. You're going to have to modify it to be able to draw lines in any direction. So I'll talk about a bit about the assignment afterwards. So just to recap this morning, with Freshening's algorithm, it's all about the error term. Okay, so at each step along, as we move along the pixels, we calculate an error, and we use the error term or the sign of the error term to determine which pixel, whether it's a pixel to the east or whether it's a pixel to the northeast, to illuminate. So here's our sort of decision, our case statement. So if the error, which is epsilon, is negative, our y-coordinate is simply the same as our current y-coordinate. So this is the new y-coordinate, yi is the current y-coordinate. If, however, the error was positive, we step up 1 pixel in the y direction. Okay, so very, very simple. The error is initialized to be equal to 2 delta y minus delta x. Delta y and delta x are the differences between the start and end points on the line. So if you've got a line joining points A and B, delta y is the differences in the y coordinate, delta x is the differences in the x coordinate. We also calculate what are the change in errors. So delta epsilon is change in error. If you've chosen to use the east pixel, the change in error is 2 delta y. Else, if you've chosen to use the northeast pixel, the change in error is 2 delta y minus delta x. Those are constant. So you only have to calculate them once, and then you can use them again. Delta x and delta y are integers, so therefore your errors are going to be integers, and all calculations involve integers. Very, very quick, very fast for a computer to be able to handle. And essentially, as I mentioned this morning, it hasn't been improved in about 50 years. So it's very, very good. Okay, as I mentioned, though, in the activity this morning, it does have a problem with steep lines. So at the moment, I've got to just explain this diagram. Okay, let this central point be our start point. I call it x0, y0, or that could be your point A. So let's say that's your start coordinate, and let this point over here, okay, where my little mouse pointer is, that's our end coordinate. So at the moment, we can draw a line in this octant of the circle. So as long as our line has got a positive gradient and it's not too steep. If we try to draw one up here, where our end point is in this octant, the gradient will be greater than 1. We'd have a problem. Likewise, if we tried to draw one down here, we may have a problem where the gradient is between -1 and 0. And so in all these other octants, so the 8 segments, or the other, 7 other octants, we have a problem. So we're going to have to modify our algorithms to be able to draw a line wherever the endpoint is. Okay, so that's a problem we have. And you can see where the gradients are. So either greater than 1, between 1 and 0, between -1 and 0, or less than -1. So we've actually only got 4 different cases, because these over here, okay, if you have a point over here, we're just drawing from right to left, and that's easily fixed. So we've only actually got 4 things to worry about, these 4 options there. As I mentioned, if you're drawing lines from right to left, that means your start coordinate is to the right of your end coordinate. Now, when we loop along the driving axis, we always just add 1 to x. So we could subtract 1 from x, but that would mean having to more programming, having if statements saying, okay, are we drawing from left to right? It's a lot easier just to swap the end coordinates. So for example, if this is my A coordinate and that's my B coordinate, so I start at A and end at B, I'll be drawing right to left. Or all we do is just swap A and B around. So B becomes A becomes B. And then you're drawing from left to right. So if you ever get a case where the start coordinate is to the right of the end coordinate, just swap them around. It's very, very quite easy thing to do. So that means we only have to worry about the right-hand side of this diagram. Okay, so if we use the DDA algorithm, which we did on Monday, to draw lines where the gradient is greater than 1, this is what we get. So these are a series of lines. This one down here doesn't look that bad. Okay, it's almost okay, but we do have a couple of gaps appearing on our lines. And as the gradient gets steeper and steeper, the gaps get bigger and bigger, and we've got dotted lines. That's no good. Okay, we want solid lines. So we have a problem. Why is this a problem, or what's causing the problem? Well, it's this. Okay, so let's assume the left-hand diagram here, we're using x as a driving axis. So here we've got a steep, our idealized line is steep. That means the change in y is greater than the change in x. Okay, so if you illuminate this pixel, step 1 to the right, and then calculate the y coordinate, we're up here. Okay, so we illuminate this pixel, and that leaves this gap. Okay, and that's because delta y is bigger than delta x, and we've chosen x to be the driving axis. To alleviate that, what we can do is instead of going across by 1 pixel and then calculating where the y coordinate is, if we go up by 1 pixel and calculate where the y coordinate is, where the x coordinate is. So y is just added, we just add 1 to y. X is what we calculate. If we do that, you can see we illuminate 3 pixels and there's no gap. So all we do is swap the driving axes. So if we have a gradient which is greater than 1, we swap the driving axis. So this is how we fix it. We do a check. Okay, so before we start our algorithm, we have an if statement. If your m, which is your gradient, is greater than 1, we change the driving axis to be y, else x. If we choose x as a driving axis, we have the standard DDA, which we saw on Monday. So your next coordinate of x is just add 1 to it. Your next coordinate of y is just add your gradient to it. If, however, y is chosen, okay, we add 1 to y, and we add 1 over m, reciprocal of m, to x, because obviously we've had to do some transposition of the equation. Right, this is this is printed on those notes, so you can probably see it in actually a bit more detail. If I was to write down the algorithm, it wouldn't fit on the slide. It's kind of quite big because we're having to do quite a bit of logic here. So I'm going to present it in the form of a flowchart. So we start at the top here. Okay, this is the start of our algorithm. We round start and end coordinates a and b to the nearest integers. Okay, so firstly we have a check. Okay, is ax bigger than bx? So this means, are we drawing from right to left? If we are, Okay, if that's a yes, we swap A and B around. Okay, and carry on. If we're not, we just carry on regardless. Okay. Now we have a check. Okay, this, notice it's got absolute value here. The absolute value of m, which is the gradient, if that's less than or equal to 1, we proceed as normal. Okay, so because it's the absolute gradient, it also deals with negative slopes. So if we've got a gentle slope, so quite a gentle slope, we go down to this one here. Okay, and this is the standard loop. So while ax is less than bx, rasterize thing, add 1 to x, add m to y, and keep going around. You keep going around that loop until you finish your line, and then you go to the end. Okay, so this is what we had on Monday, this bit here. If, however, the absolute value of m is not less than 1, that means we have a steep line. And we have two types of steep line. One's a positive slope, the other would be a negative slope. So if m is positive, okay, we go down to here. And notice what we do here is we're using the y values in our check. So this is the y as a driving axis. Okay, so rasterize it, add 1 over m to x, add 1 to y, and just keep going around this loop. Okay, so this is if we've got a steep positive slope. When we finish that loop, we go to the end. If we've got a negative slope, we do the same thing, but remember we'll be going down. So whilst y is greater than by, so ay greater than by, okay, we're going down. Okay, so rasterize, we subtract 1 over m, because we're going downhill, and we from x, and we subtract 1 from y. Okay, so this is a gentle slope, both in positive and negative directions. This is steep positive, this is steep negative. So depending on what your slope is, we got one of 3 cases. So it's just an if statement. We've got an if statement, else if, else. Okay, so that's DDA algorithm. As I mentioned, we never use DDA. Okay, it's presented here just to sort of give you a bit of background, bit of outline to line drawing. We actually always use Freshening's. So Freshening's algorithm is slightly different. Okay, first thing we're going to look at is how we deal with negative slopes on Freshening's algorithm. Okay, so if we're drawing from left to right, we do the same swap A and B as before. Freshening's algorithm for negative slopes, we choose between the pixel to the east and the pixel to the southeast. So rather than going up one, we're looking to go either across or across and down. Following on from the derivation on Monday, that should say this morning. Okay, so if I replace all of that derivation this morning with going down a pixel rather than going up, we get these. So that's our initial error. That's our error if we go to the east pixel. And that's our error if we go to the southeast pixel. Now compare those to our unmodified Freshening. The only difference is that the sign of delta y is now negative rather than positive. That makes it a lot easier. That means all of our calculations are still the same, except if we got a negative slope, we just change delta y to be negative, which makes sense. Rather than going up delta y, you're going down delta y. So that makes that bit easy. Okay. So the modifications, right, this is essentially telling you how to do the most part of question 1 on assignment 10, are just these modifications here. So if delta x is less than delta y, okay, so bx minus ax is essentially delta x. So if the absolute value of bx minus ax is less than the absolute value of by delta y, this means we have a steep slope. And what we do is we use the y as a driving axis, not the x. So all that means doing is we set x and y, we swap x and y coordinates around. So instead of having ax, ay, you'll have ay, ax. And you do the same for b. Instead of having bx, by, you'll have by, bx. So you swap the x and y coordinates around for both a and b. And what we also do is set steep equal to 1. Now, steep is what we call a flag. Okay, and I want to remember the fact that we swapped x and y around for later. So I set steep equal to 1. Steep just a variable. You could call it whatever you want. I called it steep. So if steep is equal to 1, it means we have a steep line, and it tells me later on that we've swapped x and y coordinates around. Don't forget that bit. Okay, if ax is bigger than bx, we swap a and b around. Okay, so that's drawing from left to right. If ay is greater than by, okay, so this is if we're going up or down. So if ay is bigger than by, it means we're going down the slope. If it isn't, it means we're going up. So if ay is greater than by, we negate delta y. And I've introduced a new variable called y inc. That stands for y increment. It should be +1 if we want to add 1 to the y coordinate, or it's -1 if we want to go down and subtract 1 from the y coordinate. What we then do is we go through Freshenings as normal, but when we illuminate a pixel, we check our flag. Now, the steep flag told me whether I swapped x and y around. If steep equals to 0, we didn't. So we just illuminate x and y as normal. But if steep equals 1, we rasterize yx. Because we swapped x and y around in the beginning, we've got to swap them back before we rasterize them, or before we illuminate them. And finally, when updating the y coordinate, we just use y equals y plus y inc, because y inc is either +1 or -1, depending on whether we're going up the slope or down the slope. Okay, so those are a few things we have to modify the Freshening's algorithm. Okay, and I have put a thing there that says see lecture notes for more detail. By that I mean, okay, I haven't got one of these slides, but I just put one of the got the camera on one of them. If I zoom out on page 64, I didn't put it on the slides because it wouldn't fit. Okay, I've given you an outline of the formal algorithm. So this is the modified Freshening algorithm. So if I step through this, and it start off with steep being equal to 0. If you have got a steep line, so you're checking whether you've got a steep line, then you swap ax and ay around, and you swap bx and by around. Okay, swap x and y coordinates, and flag the fact you swapped them. Okay, end ifs. So you can see this can be quite easily converted to MATLAB code. Okay, it's written in that sort of way. If ax is bigger than bx, swap a and b around. Okay, then we initialize x to be equal to ax, y to be equal to ay. Calculate delta x, calculate delta y, initialize y inc to be 1. Okay, if your ay is bigger than by, that means you're going downhill. You negate delta y and negate y increment. Okay, and then you calculate all your errors. So with the modified one, there's lots of more before we actually get to the main body of the algorithm. Once we're in the main body of the algorithm, it's very similar. Before we rasterize, we check whether steep is equal to 0. If it's not, we rasterize coordinates x, y. If it is, oh, my mistake. Sorry about this. Those two should be swapped. Eek. I'll have to make that's a quite an important fact there. Okay, so we illuminate pixel Y, then X. My apologies for that. So if we have swapped them around, before we illuminate them in the raster, we have to swap them back, essentially. Then you do the standard updating of the error. Okay, did we change the Y coordinate? Well, no, we didn't in that case, but we did in this case. And the Y coordinate is incremented by whatever Y inc is. That's either +1 or -1. Okay, that's a modified form. If you prefer it as a flow diagram. Okay, on the flow diagram, that doesn't have that error, by the way. Okay, so set steep equal to 1, we come to a decision. Do we have a steep line? If we do, swap X and Y coordinates around and flag that we have a steep line. Are we drawing from right to left? If we are, swap A and B around and then continue as before. Are we going downhill? Okay, if we are, negate delta Y and Y increment. And then we enter our standard Freshening algorithm. Okay, while X is less than BX. Okay, if we didn't flag for a steep line, okay, just rasterize X and Y. If the Y line is steep, we rasterize Y then X. Okay, is the error less than 0? If the error is negative, if it is, we update the error, add 1 to X. If it's not negative, we update the error using the delta epsilon NE and add Y inc to Y. Okay, so whichever approach you want, they both do the identical algorithm. So I will give you the Freshening. Actually, I'll bring it up now on MATLAB. Okay, so this is what I showed you before. Can you see that? Yeah, this is what I showed you at the 9 o'clock lecture. Okay, so this just assumes we have a shallow line. Okay, you're going to have to change this to take into account some of these modifications over here. Right, another thing which I'll just mention, and that's the idea of swapping coordinates. Okay, I'm going to invent 2 coordinates. Let's say A is 0, 0, and B is 10, 10. Just made 2 coordinates at the top of my head. Sometimes in both DDA and Freshening, we need to swap coordinates around. How do we do this in programming? Well, if I was to say A equals B, then A would become 10, 10, and B would still remain 10, 10. But how do I get A back into B? Because, well, I've already overwritten it. And the way I like to explain this is pretend you've got a glass of milk in one hand and a glass of beer in the other. Now, you don't want to mix milk and beer. Let's say, for some reason, you want the milk to be in the glass in the other hand. You want to swap them around. Without just swapping the glasses around, how do you do that? Exactly. Get another glass. Pour the beer into the other glass, the milk into the now empty glass, and pour the beer. Okay. So the way to do this is we get another glass. Say C. C equals A. So what I've done is I'm pouring A into C. Now, if I want to swap, A then becomes B, and B becomes C, which now has what A was. Okay, so if I return A is now 10, 10, B is 0, 0. That's a little programming trick there. If you need to swap things around, use a temporary use a temporary array. What about X and Y coordinates? So let's say D is equal to 1, 2. Okay, let's say I wanted to swap X and Y coordinates around. Very, very similar. So create a temporary, I'll call it temp. So temp would be the X coordinate. The X coordinate becomes equal to the Y coordinate. And the Y coordinate is equal to the temp, which now contains the X coordinate. As you can see, swap them around. So if you do need to do a swap, just use what we could normally call a dummy variable. Just a variable, just to sort of, it's not used in any further calculations. It's just sort of temporary storage. You could, yeah, why not? But it might cause you problems. But no. Yeah. All right. So suppose what? So you mean like D equals 1, 2, D3 equals D1, D1 equals D2, D2 equals D3. So to clear it, how would you do that? Yeah, could do just the same thing. Okay, so that's swapping. Lots of if statements. So remember if, then, else. Sorry, if, else, all that stuff. Okay, so if I go back to the slides, Okay, what I've done there is I've kept the A coordinate at the center of this raster. So my A coordinate is unchanged. The B coordinate starts here, and I just take it around in a circle. Okay, and you can see Freshening's algorithm renders can then do lines in all directions. So I created a modified Freshening algorithm, which I'm not going to show you. Yeah, so I created a modified one. Not going to show you because obviously it's your assignment. Okay, and what I've also done is instead of with the plot screen space function, which hopefully you're familiar with by now, instead of using MATLAB's fill routine, what I've done is I've applied my Freshening function to be able to rasterize the lines in my village. So this is an actually 400 by 300 pixel array, and all these lines are actually Freshening algorithm lines. So if you think about this village, we've gone right from primitive objects, your house, your tower and stuff. We've gone through all of the transformations, rotation, scaling, translation, aligned to the world space, projected, clipped, and now drawn on our raster. So this kind of gone from all of the steps in the graphics pipeline. Notice I haven't done any hidden surface removal on this, because that comes with filling polygons, which we'll look at in a couple of weeks. Haven't done any lighting, texture mapping. That's still to come. Okay, right. I'm just going to stop the recording there, and